This lesson is all about ionic bonding, section 8.2 in your book. And so the goals today are to define ionic bonding, learn how a Lewis dot structure changes as an atom becomes an ion, and then understand the relationship between a term called lattice energy and Coulomb's law. So our definition of ionic bonding is a bond that occurs between oppositely charged ions. The ions are formed by the transfer of one or more electrons. So that means we have two atoms. One of the atoms is going to have a low ionization energy. So if you remember, that would be a metal, something down and left on the periodic table, and then something that's going to be non-metal, which would have a higher ionization energy, but would also attract electrons. We would say that it has a high electron affinity. So the combination of those two is going to provide for a pretty violent reaction, as I'm going to show you in this video clip. So we just saw that video of what the formation of salt from sodium and chlorine looks like. From a Lewis dot structure standpoint, you can see what it looks like. It's pretty simple. We have sodium that has 1 valence electron and low ionization energy, chlorine that has 7 valence electrons and high ionization energy, and so the sodium gives up that electron to chlorine, and the result is that both sodium and chlorine now have an octet, which is very stable. Even though we don't see 8 dots for sodium ion, the sodium ion now has completed first and second energy levels, so it does have the octet. And then you can see how we represent a negative ion with brackets followed by the charge. And so this is an important concept for drawing Lewis dot structures. This slide shows the process for what's happening. If you look on the left-hand side, you can see that the sodium solid is in a nice crystalline pattern, and we have chlorine gas. When the sodium was introduced to the chlorine gas, you could start to see that there are electron transfers occurring between sodium and chlorine. And once there was enough energy, we started to see that light being given off and all that heat. And the result was we have a sodium chloride crystal. This picture is on page 291 of your book, and what I want you to notice is we've got that reaction equation represented, but off to the side, here you see what the finished product looks like. Sodium chloride is a repeating pattern of sodium ions and chloride ions, and one of the other things that I want you to notice is it's cubic, and let's think about the attractive forces that are occurring within this crystal. We have positive and negative ions, so that's electrostatic attraction. And in Coulomb's law terms, we have these ions very close together, so there's not much distance. That'll make a strong attractive force. We also have our positive and negative charges. Those are the two particles. Those are the Q values. And if you would go within this structure, you would see that every ion is surrounded by 6 ions of the opposite charge. So that means that there's an even greater effect due to the Coulombic attractions, and that's going to result in a whole lot of heat given off because we've gone from a large degree of chemical potential energy down to a smaller amount of potential energy, and all of that excess energy was released in the form of heat. This brings us to the concept of lattice energy. So if we wanted to take that salt crystal that we just saw and we wanted to completely separate all of those ions, and technically we're separating them into gaseous ions, so in a gaseous state. How much energy is that? That's what we'd call lattice energy. And that's a whole lot of energy. And you can see, again, that we can use Coulomb's law to predict the kind of lattice energies that different compounds would have. So take a moment and study this table. And what I want you to study about it is what is the relationship between the variables in Coulomb's law and these lattice energies. So specifically, what is the relationship between the charge and lattice energy, and what is the relationship between the atomic or ionic radius and the lattice energy? Do you notice, for instance, that lithium fluoride and magnesium chloride, which are both fairly similar in size, not too much difference, but because magnesium chloride the magnesium has twice the charge, we see about twice the lattice energy. We'll also notice that there are smaller lattice energies as the salts, these ionic compounds, get even bigger. So that's another trend that we can follow. Bigger radius, less attractive force. Larger charges, more attractive force. So in summary, ionic bonds are formed between metals and nonmetals, and they're very exothermic reactions. We also saw how a Lewis dot structure changes when atoms come together to form an ionic compound. And then we also saw the idea of lattice energy, which is very endothermic, requires a lot of energy, and it depends on those aspects that we saw in Coulomb's law. So this is the end of 8.2. Let me know if you have any questions.